Right, in this video, I'm going to go through the A-level chemistry paper, OCR A-level chemistry paper from 2021, and this is paper 2. Okay, and I'll do this paper in two halves, first half in this video and second half in a later one. Okay, so we start off with the multiple choice section. 2-methylbutane is reacted with chlorine, okay, by radical substitution. The number of structural isomers with this formula. So we have just substituted one hydrogen with a chlorine. So how many different isomers? Well, we could stick the chlorine on either of those two carbons. That would be the same. So that's 1. Or we could have it on that one. That'd be 2. Or we could have it on, that'd be 2. Or it would go on that one, or it could go on that one. So 4 different isomers. The answer to that one is C. Okay, which types of stereoisomerism are shown by 2,4-dimethyl-hex-2-ene? So I've drawn the skeleton of it there. Okay, 2,4-dimethyl-hex-2-ene. Right. Can that show optical isomerism? Yes, it can, because we would just have a look at that carbon there, number 4. What it's got attached to it, it's got an ethyl, a methyl, this group, and a hydrogen. It's 4 different groups attached to that carbon, so it can show optical. Now let's have a quick look at see if it can do. We've got a double bond there. Can that do EZ isomerism? Well, it can't, because if you look at this carbon here, you've got this one here, you've got 2 methyl groups, 2 the same. So when you have 2 groups the same on one carbon, you can't have EZ isomerism. So B is the answer to that one, only optical isomerism. Okay, so this is, try and find a quick way of doing this. Which sample contains the greatest number of carbon atoms? So we forget about the atoms, we number of moles of carbon, okay? Moles of carbon atom. Mole, okay. That there really, shouldn't I? Moles of carbon. Right, so let's do, how would we do A? Moles of A is equal to mass over MR. So the mass is 20 grams, and the MR, well, that is C6H5OH. So that has got an MR of 94, okay? So that's 20 over 94. So that's the moles of the compound. So how many moles of carbon atom have we got? Well, it's the number of moles of the compound, which is 20 over 94, multiplied by the number of carbons in the molecule, which is 6. Okay, so we've got to do that for each of them. So let's do that. That's for A. Let's do it for B. So for B, we would do the mass, which is 30 grams, over the MR of, now that is C2H5. What is the MR of B? Is 60 plus 14. That is 74 propanoic acid, multiplied by 3. Let's do C. So for C, we've got 40 is the mass over the MR of, that's ethanol. Ethanol has got an MR of 44. There are 2 carbon atoms in there. And then finally, let's do D. So we've got 50. The MR of methanol is 32. And there's only 1 carbon in there, so it's times 1. So let's just roughly see what that is. Okay. Right. So 20 over, that works out to be 1.27. Just doing a calculator. Okay, B is going to be equal to Right, it's going to be about 1.5, that, isn't it? I think 30 divided by 74 times 3, 1.2. It's about 1.2. Now this one, C, is definitely going to be bigger. 40 over 44 times 2, that's about 2. So that's got the most number of moles of carbon so far. And can D compete with that? Well, it can't, because 50 over 32 times 1, that's just over 1. So C is the right answer there. Without calculating everything, I think you've got to try and be a little bit quicker with those sort of questions. Right. What is the correct equation for the incomplete combustion of butane 1-ol? Right, now anything we're making hydrogen is definitely wrong, because you never get hydrogen in incomplete combustion. You always get water, you never get hydrogen. So they're wrong. They're wrong. So C and D are the only possibilities. So let's see, on this side of the equation, we need 9 oxygen atoms. We've got 1 in the butanol, so that means we need 8. So 4 molecules of O2, that's the correct one. Okay, this one here, yeah, you'd also need 9 oxygen atoms. You've got 9 there, haven't you? But you've got 1 there as well, makes 10 on the left-hand side. So C is the right answer there. Okay, 2-methyl cyclopentanone can be reacted with a cyanide ion. Okay, so of course what's going to happen here is the cyanide is going to nucleophilic attack. It's going to attack that carbon, so you're going to end up with, that is going to go to, let's draw the product. Well, that is going to turn into an OH, and the cyanide is going to stick onto that there. So that is the product you're going to have here. Okay. In the mechanism, the cyanide ion accepts an electron pair. That's wrong. It actually donates a lone pair, doesn't it? It is a nucleophile. That lone pair attacks that carbon there. That's what happens. It's electrophilic addition. It's wrong. It's nucleophilic addition. Cyanide is a nucleophile. The organic product has 1 chiral center. That is not correct, because look, that carbon is chiral. You've got OH, CN, and 2 different carbons attached to it. And this carbon here is also chiral. You've got an H attached to it there. You've got a methyl, and you've got that carbon and that carbon, they're the same. So there's 2 chiral centers in that, so that's wrong. So the last one must be correct. The organic product has a molecular formula C7H11NO. Well, it's got the right number of carbon atoms. Yeah, you count. It's got 7 carbons, got 1 oxygen there. It's got 1 nitrogen. Count up the hydrogens. 1, 2 there makes 3, 2 there makes 5, 2 there makes 7, 1 there makes 8, plus 3 is 11 hydrogens. Yeah, that is the right molecular formula. It's the only one that could possibly be right as well. Okay, so we have got this, which is, you can see this is an ester. All right, just draw it out. What does it look like? Okay, it looks like that. It's methyl ethanoate. Now, if you hydrolyze it with aqueous sodium hydroxide, you're going to split it up, aren't you? You're going to split it up into that. That's going to give you methanol there. And you're going to get not the carboxylic acid, because it's under alkaline conditions. You're going to get the salt of the carboxylic acid. You're going to get that, aren't you? Okay, so A is wrong because you've got the carboxylic acid there. That's wrong. B is correct because look, we've got the salt, the minus, and the plus on the sodium there. That is correct. Why is this one wrong? Well, you don't form that sodium methoxide. That doesn't form, and again, that compound doesn't form there. So B is the correct answer there. Okay, menthol is heated with an acid catalyst. Now, what's that going to do? It's going to dehydrate it. So when you dehydrate, right, you remove the OH and a hydrogen from the carbon next door. Now, you've got 2 next door carbons. You've got that one there, and you've got the blue one. So there's two possible products for dehydration. Now, if you remove, let's see, if you remove a hydrogen from the green carbon there, you're going to get that. The only thing is they've drawn it the other, they put the double bond on the other side, yeah. But that A is correct. B isn't correct. You couldn't get the double bond forming. You couldn't get the double bond forming up there, could you? Because it forms between the carbon with the OH on it and the one next door to that. Well, the OH isn't attached to either of those carbons, so that's wrong. The OH again for C is wrong. The OH is not attached to that carbon or that carbon, so you can't get a double bond forming there. And well, D is actually the same thing as B, isn't it? It's just drawn back to front. So A is our answer there. Which compound contains a bond angle of approximately 120? Right, now, in order to have that, we've got to have one of our carbons really has got to be forming a double bond, okay? Because if it's forming 4 bonds, of course, the bond angle is going to be it's going to tetrahedral shape. It's going to be 109.5. So we want one with a double bond in it. Well, A's got a triple bond, but no double, so that's not right. There's no double bond in B, impossible. There is a double bond here in C, and there's no double bond in D. So C is the answer. If you just look at, so C, if you draw it out, C is going to be like that. And all the bond angles around that carbon, they're all going to be 120 because there's 3 bonding pairs and there's no lone pairs in the carbon. D is the answer there. Okay, which is not a reduction? Well, in organic chemistry, very often we say reduction is either remove oxygen or add hydrogen. That's reduction. In organic chemistry, we don't usually use oxidation numbers. Well, you can see A is a reduction because you have removed oxygen from the, and you reduced it to an amine group. That's a reduction. This one is a reduction B because you've added a load of hydrogens onto the carbon and the nitrogen there to form the amine. C is not a reduction because it's nucleophilic substitution. You swapped a chlorine for an NH2. So this is the one that's not a reduction. Is D a reduction? Yes, it is. What we've got there, we've got a ketone. That's a ketone there. And we're reducing it to there, which is a secondary alcohol, adding hydrogens onto it. Okay, so C is the answer there, the only one that's not a reduction. Okay, TLC chromatogram for 2 compounds, shown below. What is the RF value for the compound that is most strongly adsorbed onto the stationary phase? Now, we don't actually have to do any working out here, which is the one that's most strongly adsorbed to the stationary phase. That's going to move the least far in the solvent. So it's going to be that spot there. Okay, what's RF? Is the distance of the spot over the solvent front. And so the I think if you measure that one up there, it is closer to 0.25 rather than 0.33. These two are obviously way too high. If you put your ruler on it, A is the answer there using that formula. A is our answer to number 10. Okay, infrared spectrum shown below. Now I've also just pasted in the data book. We probably used to doing this without the data book. You should know that all of that stuff there is the fingerprint region, so we're going to ignore that. And your eye should be drawn to this here. All right, this bit here. That is due to an alcohol OH, okay? And that is the OH. Characteristically, it's very close to this is actually CH, and that's why you get 2 peaks. If you just look OH for an alcohol, is it in the right region? OH alcohols, yeah, 3,200, yeah, so that's about 3,400. That one is in the right range. So we've got an alcohol in there. And the other thing, which is fairly obvious, is this big deep peak here, which is very characteristic of a carbon oxygen double bond, the carbonyl group, which is that's in the right region as well. So we want one with an alcohol and with a carbonyl in it. So D is the answer there. Okay. Some people may think that this is due to a carbon-carbon double bond because it is pretty close. If you look carbon-carbon, it's like, yeah. I think if you check it is just a little bit too, it's a little bit too high. It's about 1700, that. It's a little bit too high for alkenes, okay? Also, if you've seen a lot of this spectrum, you'll realize that the alkene, you don't get such a deep peak with an alkene. You get a little sort of sharp, shallow peak, whereas this long, wideish, deep peak is very in that region, about 60 and 80, is very characteristic of a carbonyl. So there you've got a carbonyl group there, and you've got the alcohol group there in D. Okay, right. Mass spectrum of propanol which would appear in the mass spectrum of propanol, but not in a propanone. Now, these are obviously, they've both got an MR of what is it? It is 30. They've got MRs of 58. Okay. These are that one is the parent ion there. Well, that's going to appear in both of them, so that we can rule that one out. And the others are due to fragments. Right, can a 15, okay, let's see a 15, a fragment with 15, that's like a methyl group. Right, they've both got methyl groups, yeah. Methyl there, so that you'd expect that in both of them. You could produce that fragment quite easily. 29, the next one. Right, that is characteristic of an ethyl group, CH3CH2. And you can probably see there, look, you can get an ethyl group in that one, in the propanol, but you can't get an ethyl group in, there's no ethyl in propanone. So B is our answer there. And let's just check the 43 thing. Okay, now 43, I think they can both give you 43. That there adds up to 43. And I think that there, that also adds up to 43. So you can get those two fragments. So they both produce a fragment of 43. The one we want there is B. Okay, 13. Which compound has 4 peaks? Which ones have 4 peaks in the 13C spectrum? Okay, let's see. So you've got one there. Those two green ones are the same. Those two blue ones are the same. And that one I just draws an open circle. That's different. So look, you've got 4 different peaks there. Yeah, so you can have that one. That's got 4. These are all unique, those carbons. That's different to that one, to that one, to that one. That will give you 4 peaks as well. Let's check the last one. Right, we've got those 2 methyls, they're the same as each other. We've got those 2 carbons there, they're the same as each other. And if you look at all the other carbons, all of these are all the same as each other. So that would only give you 3 peaks. So the answer is 1 and 2. So it's B. Okay, 14. Which of the following statements provide evidence for the delocalized model of benzene? Right, now the first one is the trickiest. The enthalpy of hydrogenation is more exothermic, and it's not, it's actually less exothermic, because benzene is more stable than you would expect it to be. So that one is wrong. That's not right. 2, benzene only reacts with bromine in the presence of halogen carrier. Okay, that's correct. If it was a K-Kool-Aid structure, if it did have genuine double bonds in it, then it should react with bromine without any catalyst, without the halogen catalyst, and it doesn't. So 2 supports it. And 3, the carbon-carbon bonds all have the same length. That is correct, because in that's the delocalized structure, yeah, because each bond, if you like, is like a 1.5 bond, whereas if it was a K-Kool-Aid structure, the doubles would be a bit shorter than the singles, so they wouldn't all be the same length. So 2 and 3 are correct there, so we've got C. 15, okay. Right, which ones will react with NaOH? Well, phenols are acidic, aren't they? Yeah, you will lose that. That proton is a bit acidic, unlike alcohols, and form a minus there. Of course, because that negative charge is partly delocalized in the ring. So normal alcohols, they're not noticeably acidic. Phenol is a little bit, it will react with OH minus. This is a carboxylic acid, yeah, that will lose that H to form that will react. And will OH react with this? Well, it will do. OH will act not as a base this time, it's going to act as a nucleophile, it's going to attack that. You get nucleophilic substitution. So 1, 2, and 3 is the answer. So A is the correct choice. Okay, that's the end of the multiple choice. I'm going to switch over to the other questions on a new whiteboard. So, okay, let's get to the start of this. Question 16. Okay. Right, so we've got but1-ene and but1,3-diene are unsaturated compounds. All right, but1-ene and but1,3-diene have sigma bonds and pi bonds. What is meant by the term sigma and pi? Well, the sigma bond is formed by the overlap of two orbitals, and the electron density is between the carbon atoms. Whereas the pi bond, well, this is formed by the sideways overlap of p electrons. And you get the you don't get the electron density between the atoms, you get it above and below the carbon atoms. Right, how many sigma and pi bonds in one molecule of but1,3-diene? So I've drawn it there. Well, let's just, don't forget, a double bond is made up of one sigma and one pi bond. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds, and the number of pi bonds, well, that's easy, just one there and one there, 2 pi bonds. Okay, but1-ene is reacted with hydrogen bromide. This is a mechanism forming a mixture of two saturated organic compounds. Okay, to get rid of the double bond. One of the organic products is found in much greater quantity. Okay, outline the mechanism for the formation of the major organic compound. Now, just to remind us, what's going to happen is we're going to stick a hydrogen onto one of those carbons, and we're going to stick the bromine onto the other. Now, the way I've drawn it there, that is going to be the major product, because if you remember, the major product, the hydrogen, will stick on, the rough way of remembering it is the hydrogen will stick onto the carbon that's already got the most hydrogen. So that carbon there has already got 2 hydrogens, so it's going to go on there in the major product. That carbon there has only got 1. So you see. Okay, so that's how you can kind of remember what's the major and the minor, although it doesn't explain what the major, why there's major or minor, but we'll do that later. Right, let's do the mechanism then. So we've got HBr comes along. It says include dipoles. We've got a permanent dipole there. This is delta positive. This is delta minus. The first step in the mechanism is for the pair of electrons in the pi bond to go onto the hydrogen. And then the bond between the bromine and the hydrogen has got to break. Okay, and don't forget, we're going to have that blue hydrogen sticking onto that carbon there. So let's do that. So that is, and we've got the ethyl group here, a hydrogen, And this carbon has now got a positive charge in it. That's a carbocation. And just to remind ourselves, that is actually a secondary carbocation, isn't it? Okay. And that's why it's probably going to ask us about this later. That's why I'm mentioning it now. So that's a secondary carbocation. Then the final step in that mechanism is for the bromide ion, which is formed here with a lone pair. That goes onto there. And that is going to form the product, which is going to be like that. Okay, so that's our marks for that. Next part of the question, then it's going to say, explain why one organic product is formed in much greater quantity than the other organic product. Right, okay, right. I'm going to explain it up here. It's because this, the major one, is formed from a secondary carbocation. The minor one would be formed from, in this case, from a primary carbocation. I wouldn't bother writing the answer, but just to explain to you, I just write down what would that primary carbocation be. It would be like that. So we stuck the hydrogen onto that one there instead. So we've got a positive charge on that carbon. That's the primary carbocation, right? So why, and the primary carbocation, this is less stable. Why is it less stable? Is because the alkyl groups have a tendency to push away electrons towards the positive charge. So you've got one alkyl group there, you've got two alkyl groups there, both are pushing a bit of charge towards the positive charge on the carbon. Whereas if you look at the primary carbocation, you've only got one alkyl group pushing charge in there. Okay, so the positive charge is more intense on that carbon. Okay, it's only I think it was 2 marks. So I think you just need to say the major product is formed through the secondary carbocation, which is more stable. That's all you have to say. But I just explained it a bit more for you, in case you weren't sure on that. Can I say the classic wrong answer is that it's the stability of the carbocation intermediates. It's not the actual product. So the wrong answer, people say that the minor product itself is less stable. But it's not. It's the same stability as the major product. It's the stability of the carbocation intermediates. Okay, moving on. Butyl-1,3-diene is reacted with an excess of hydrogen bromide, forming a mixture of saturated. We're going to react both double bonds. How many saturated products can be present in this mixture? Well, let's just draw butyl-diene here. So let's call them 1, 2, 3, and 4. So an HBr is going to react with that double bond and that double bond. And of course, the H or the Br can stick onto different carbons. So let's see one product we can have. Let's say that the Br has gone on that carbon and the Br has gone on that carbon. Of course, H has gone on that one and H on that one. So that's a possibility. Alternatively, we could have the Br, that's the same, but this time the Br goes there. And then the third possibility, another possibility is going to be if the Br goes on that one or on that one. So they're the only 3 different alternatives that you can have there. So there's 3 possibilities. Okay, 3 of them. Of course, if I said, save me drawing it out again, if I said, like, you could have the Br going on that one and that one, well, that of course is exactly the same as that one there, isn't it? It's not a different thing. Okay, so 4 is the answer there. Just get rid of that. Okay, right. A student thought that butyl-1,3-diene can show stereoisomerism, and they drew out the skeletal formula like that, and actually they're wrong, aren't they? Okay, what's the meaning of this term stereoisomerism, and you used to learn that. It's just learn the definition. It's the same same structural formula and molecular formula, but different arrangement of atoms in space. Okay, learn that. Okay, and of course, there's two kinds of stereoisomerism which we come across at A level. There's EZ isomerism, which and there is optical isomerism. Okay, explain with the reason whether the student is correct or incorrect. Well, he is incorrect, isn't he? This buta-1,3-diene doesn't show EZ isomerism because look, we draw it. That carbon there has got two hydrogens attached to it. It's got the same things attached to the carbon. So you can't have stereoisomerism across that particular double bond. Okay, let's look at the other double bond. I'll write that way around actually, so space. Right, we've got another double bond, but again, that's the same as well because you've got two hydrogens attached to the carbon on the end there. So that one, you can't have two arrangements around that double bond. So the student is incorrect because these carbons both have two identical groups stuck to them. So no EZ isomerism is possible. Okay, here's this Diels Alder reaction, okay, which is, they're telling you what it is. You don't need to know about it beforehand. And so you get you get butadiene and ethene, and you'll form cyclohexene there. Right, add curly arrows in the diagram to complete the mechanism. Okay, so that curly arrow is going to go there, and that's going to form this new single bond there. Okay, you can see that this double bond has gone, and where's it gone to? Well, so that has gone to form the new double bond between those two carbons, and then this double bond also, that's not a double bond anymore, is it? So what's that done? Well, that has gone like that to form between those two carbons to form that single bond. So that's what's gone on there. Right, two more of these reactions are shown below. In the boxes, draw the organic product of each reaction. But we're just going to try and copy what happened in that thing up there then. So that is going to go like that, and it's going to form a new bond there. Red. Going to form a new bond there. This double bond is going to break, but to form a new double bond there. And that double bond is going to break to form a new bond there. So we draw the structure of the new thing. What's it look like? Well, we've got a new double bond there. Oops. And that double bond's gone there. And we've got nothing has changed to that part of the molecule there, the ester bit there. Ester bit there. Okay, so that's the first one. Do the same again for the second one. Okay, so what we're going to do, we are going to have, right, this time it's a triple bond. So the pi bond, one of the pi bonds in the triple bond, remember triple bond, you've got two pi bonds. That one is going to go and form a new single bond between those two carbons. This double bond, that's going to go there. And this one is going to go there to form a new single bond there. Okay, so what's it going to look like, the product? Well, we're going to have a new double bond there. Okay, and we're going to have, right, that we've still, the triple bond's gone, but it's a double bond, only one pi one broken. And then we've got these two methyl groups, which is probably best to draw them like that. Okay, so that is our product for that one. Okay, question is about haloalkanes and polymers. Freon is a CFC with a molecular formula there. In the upper atmosphere, the presence of Freon can lead to ozone depletion. Explain with the aid of equations how Freon can lead to ozone depletion. Right, so first of all, we're going to get free radicals going on here, aren't we? So the UV light is going to break the bond between, let's just draw it like that, so it's going to have 3 fluorines. It's going to break that bond between the carbon and the chlorine, so let's draw that. So ClF3 is going to give us CF3, that's a free radical, and a chlorine free radical. It's got an unpaired electron on the chlorine. The chlorine is then going to react with ozone, which is O3, to form a new free radical. Now, the unpaired electron is actually on the oxygen there. Look in the mark scheme though, and they have drawn it, for some reason they've drawn it on the chlorine, but if you draw a dot cross diagram for that, I would prefer to put the unpaired electron there on the oxygen, and that's going to leave O2. And then you get further reactions occurring, and that can then react with another ozone molecule to give a chlorine free radical and 2 oxygens. Okay, so you can see it doesn't really ask us there, but you just have to write those equations. But of course, the chlorine free radical is regenerated. It's used up first of all, it's regenerated there. So it's essentially acting like a catalyst, causing the depletion of ozone. Okay. An oligomer is a polymer with a low molecular mass and a small number of repeat units. An oligo is made from 2-chloro-1,1,2-difluoroethane. Let's draw that out. So what does that look like? It's got fluorines on carbon number 1, 1 fluorine on carbon number 2, and a chlorine on carbon number 2. How is that going to polymerize? Well, you're going to get another one, the same next to it, aren't you? And you're going to break the double bonds. And you're going to form a new bond between these carbons. Okay, so, but it's only asking us 1 repeat unit. I've drawn 2 there, so we need to rub some of that out. Otherwise you'll be penalized, you won't get the mark. So that is the repeating unit, like that. Okay. I usually put brackets around the repeating unit as well, but sorry. Don't think you have to, but I prefer to. Right, the boiling point of the lubricating oil can be increased by increasing the number of repeat units. Okay, how does that going to increase the boiling point? Will it make the molecule bigger? Obviously. Which will mean you have more electrons, more points of contact, so the London forces will be bigger. That's induced dipole-dipole interactions. That'll make it bigger. A polymer can be made from the monomers, 1,4-diaminobutene, okay, and benzene 1,4-diacyl chloride. Draw the structures and 1 repeat unit of the polymer. So let's draw diaminobutane first of all. So we're going to have an NH2 at one end. 4 carbons. Okay, so that is going to be 1 of the monomers, diaminobutene. Now benzene 1,4-diacyl chloride, so that's going to have a benzene ring. Sorry. And we're going to have ethanol chloride at positions number 1 and 4. So that's number 1. And the same on number 4 on that end there. Okay, so we've drawn our 2 monomers, but we've got 2 marks for that. let's draw how the polymer, the repeating unit. So how's that going to work? Right, I'm just going to change that to put displayed formula. Right, so what happens is we're going to lose the hydrogen chloride there, aren't we? Yeah. We're going to form a new bond between the nitrogen and the carbon. So we form a new bond there. Okay, and the same thing happens at the other end. So I would draw. Right, and that's going to form, yeah, going to get the same thing going on there. And the same thing is going to happen at this end. So you're going to have, right, and that's going to form onto, yeah. Now it asks us for one repeating unit, so I should start off there and I should finish there. So I should rub those bits out, but quite often I just put them in. It's a good idea. It helps you, stops you making a mistake and drawing the polymer. Okay, so there is a repeating unit of the polymer. It is a polyamide. Okay, of course, yeah. Addition condensation polymer, sorry. Okay. Question 18. This is about organic acids. So we've actually got 4 amino acids there, and they give us the R groups. Okay. Explain the term optical isomerism. Well, optical isomerism, you have 2 non-superimposable mirror images. That's what optical isomers are. And of course, they arise by having 4 different groups attached to 1 carbon atom. So that's the definition of optical isomer. And we should draw 3D diagrams to show the optical isomers of alanine, the amino acid. So just so the R group alanine is that. Just to remind us, what's all amino acids like? So we have carboxylic acid at one end, we have an amine at the other end, and here we have the R group, which in the case of alanine is CH3. So which is the asymmetric carbon here, the one that gives rise to optical isomerism, is this one here, because you've got 4 different groups attached to it. Now we've got to draw some 3D diagrams. So we draw that carbon here, okay, and that's a tetrahedral carbon. So I'm going to draw one group coming out of the plane of the paper, the CH3. We'll have this NH2 going into the plane of the paper, dotted line. We have this is in the plane of the paper, that's the carboxylic acid group. And we have this one sticking up in the plane of the paper, the hydrogen. Okay, so that's one there, and we need to draw a mirror image of that. So if we draw, there's our imaginary mirror. We're just going to draw the mirror image of that. So this time we're going to have the carboxylic acid there, the methyl there, the NH2 there, and the hydrogen there. And those two are not the same as each other. They're mirror images and they're non-superimposable. Okay. Right. Next question. How many optical isomers does threonine have? Now, this is the R group for threonine, okay, which they gave us in the table earlier. So I'll just draw out threonine. It's going to be, so we've got the carbon, which has got the carboxylic acid attached to it, carboxylic acid group, the amine group, and in the case of threonine, we have got CH, OH, CH3. Now, you can probably spot now that there are 2 asymmetric carbon atoms in that molecule. You've got one there, the green one. So 4 different groups attached to that. We've also got this one, the red one here, that is also asymmetric. So there are 2 asymmetric carbons. Each one can give rise to 2 different configurations around it. So 2 times 2, the total number of isomers you can get, of optical isomers you can get, is 4. There are 4 possible optical isomers of threonine. And of course, you only ever get one in life, in living things, but there are 4 possible isomers. Right, so here we have got complete the flow chart for the synthetic routes to the amino acid valine. Now I've just done that bit there. That is the whole page, and obviously I can't write on that, it's too small. So I've chopped it up into two kind of halves. Okay, so let's have a look at this bit here first. Okay, so we've got an ester, which is C7H14O3. And we've turned it into a carboxylic acid and an alcohol, and that has got, that's C5H10O3. So you can see there, what have we lost? We have lost 2 carbon atoms. And we have lost, we lost 4 hydrogens, okay? So so there's obviously something with an ethyl group going on there, and you can probably see that that was probably, you've got this alcohol, and that's going to form an ester linkage to the carboxylic acid group there. Okay, so let's just draw that in the box. So you started off with an ester and you hydrolyzed it to the carboxylic acid. So the ester is going to look like this. It's going to be the same. That alcohol is the same. You've got those 2 methyl groups, that's the same. But instead of a free carboxylic acid here, we had an ester with 2 carbons in it. Okay, so that is the ester there. It's an ester between the carboxylic acid and ethanol. Now, how would you hydrolyze that ester? How would you get rid of, how would you break the ester linkage there and then with the carboxylic acid? Well, you would, you can't use alkaline hydrolysis because you wouldn't get the carboxylic acid, you'd get the OH, you get the O minus there. So it must be acid hydrolysis. So we want probably hydrochloric acid, and you would heat, you'd boil it in hydrochloric acid, and you would hydrolyze the ester. Okay, let's have a look at this bit here. Well, we've turned an acyl chloride here into a carboxylic acid. Okay, so you've got rid of the chlorine and turned it into carboxylic acid. How do you do that? Well, you just react it with water. What's the acyl chloride going to look like? It's obviously going to look like this. Okay. You can have that instead of an OH, you can have a chlorine there. And that, of course. So that's what the acyl chloride looks like. And literally just water, you don't need to heat it up or anything, it just reacts very quickly with water to hydrolyze the acyl chloride into a carboxylic acid. Right, so we've done this top bit, and now I'm going to just do this bottom bit now, okay? Down below. Okay, so we've done the acyl chloride bit. I'm not going to fill that bit in again, we've already done that. But here, well, what are we doing? We are turning, and it might be easier to work backwards here. Okay, so what have we done here? We've got a haloalkane, and we've obviously replaced that bromine with an NH2 group, I think there. Okay, now what would you use for that? You would use an excess of ammonia. Right, so let's draw the haloalkane. What's that going to look like? Well, it's going to look the same as that, except it's going to have a bromine where that amine group is. Got bromine there. Carboxylic acid. Okay. How do we turn this thing into the haloalkane? Well, all we've done is we replaced an alcohol group with a Br atom. How do you do that? Well, you need sodium bromide It's nucleophilic substitution, essentially, but you will also need a sulfuric acid catalyst. So you change the alcohol into a haloalkane. Right, ibuprofen. I've got the structure of ibuprofen there. What's the molecular formula of ibuprofen? Well, let's do this. We're going to count up the carbon atoms. So I've got 1, 2, 3, 4. We've got 6 in the ring. So 4 plus 6 makes 10, 11, 12, 13. We've got, now, rather than do the hydrogens individually, there's a bit of a quick way of doing this. You look for, so if it, well, let's do it the long way around. What we've got 3 there, we've got 3 there, 3 there, 1 there, 2 there. We've got 1 there, 1 there, 1 there, 1 there. None on that carbon there. We've got 1 on that carbon, 3 there, and 1 there. So what that adds up to 18. And then how many oxygens have we got? We've got 2. C13. Right, there's a bit of a quicker way of doing that, right? You know, I'll just rub these out. If you've only got carbons, hydrogen, and oxygens, this will work. If you've got nitrogen in the molecule, it won't work. But what you do is you do like C13. Now, if it was CnH2n plus 2, you would need 28 hydrogen atoms there, wouldn't you? But every time you have a double bond or a ring, you lose 2 H's, okay? So for every ring you have, you also lose 2 H's. So how many effective that double bond, that benzene ring is, you've got 3 double bonds there and a ring. So that's 4 lots of 2 hydrogens, and you've got another double bond that's 5 lots of 2 hydrogens. So we're going to lose 10 hydrogens. So it's not H28, it is H18, which is the number we've got there. So a bit of a quicker way of doing it. If you've got it for that one, it doesn't make much difference, but if you've got a much bigger molecule, it can save you time. So C13H18O2. Right, 1 ibuprofen tablet contains 400 milligrams. Calculate the number of molecules in 1 tablet. Okay, so we need the formula, which was, what was it? It was C13H18O2. That's the formula of ibuprofen. So the MR is that, you work it out, that's going to be, that's 206. Right, moles, first of all, we want to look up the number of molecules, we have the moles, then multiplied by the Avogadro constant. So moles is mass over MR. The mass, we have got 400 milligrams, that's 0.4 grams, over 206. That works out to be 1.94 times 10 to the minus 3 moles. Now, number of molecules, you're going to multiply that by the Avogadro constant. So molecules is going to be equal to 1.94 times 10 to the minus 3 multiplied by the Avogadro constant from our data book, 6.023 times 10 to the 23. That gives you 1.689 times 10 to the minus 10 to the plus 21, sorry. Right, it asks us to go to 3 significant figures, so we should write that down as 1 point, sorry, I missed a 1 out there. So that, so 3 significant figures, that will be 1.17 times 10 to the 21 molecules. Okay. Right, tablets based on ibuprofen and lysine, which is amino acid, are now available from pharmacies. These tablets are claimed to act faster by being absorbed into the body more quickly. Okay. One type of these tablets contains a salt of ibuprofen and the amino acid lysine in a 1-to-1 molar proportion. Suggests the structure of each ion in this salt. Now, the reason why it's thought that they should act faster is because if they are charged, they are more soluble in water, which is a polar solvent. Okay, so they're going to, of course, you'll get into your bloodstream more quickly if it's more soluble. Right, so now we need to write down the structure of the amino acid lysine. So it's got that. So I'm going to draw what's lysine going to look like. It's got the carbon attached to a carboxylic acid group. It's got an amine group there. And then you've got 4 CH2s, and you've got another amine group here. Right, let's have a think about what kind of ion could ibuprofen form. How could that form an ion? Well, it's got a carboxylic acid on it. So if you lost that hydrogen there, if you remove that and turn that to a negatively charged, okay, so that's going to be the negative ion of ibuprofen. Now, so that means the lysine must form some kind of positive ion. And here, look, it says it's in a 1-to-1 molar proportion. So that means it must be just a 1+ on the lysine. Because when I first looked at this question, I thought, oh, well, if the lysine, the lysine has got 2 amine groups. You could protonate it there. Okay. And you could also protonate it there. And that will give you 2 positive charges. But that would mean then that the ibuprofen, you need 2 lots of ibuprofen for 1 lysine. The question says it's a 1-to-1. So that means we must only have 1 positive charge on the lysine. And I wouldn't really think that there's much of a difference between either of those two. Which of those 2 nitrogens is easiest to protonate? I would think they'd be the same. And I thought, right, let's do that bottom one then. Okay. And I looked in the mark scheme, and yes, you can have that one, but the one that it said first was protonated on that one. So that doesn't really matter, I don't think, but and I don't think I can't think of any reason why one of those, they should be roughly the same basic strength, same ability to attract proteins, but that's the first option in the mark scheme. But it says you could also have the positive charge on there as well. Okay, suggest why tablets based on a salt of ibuprofen should act faster in the body than well, I said that before, isn't it? It's because they are charged. The ibuprofen is charged, so that means it is more soluble in polar solvents such as water, which is of course basically what your blood is, water. So it's going to be more water soluble, so it'll be absorbed more quickly. Right, now that is the end of question 18, and that's where I'm going to, about halfway through that paper, I'm going to stop there and carry on this paper in the next video.